Hello, in this video we will define finite element analysis. We will also see where this method is used and familiarize with some of the basic terms. Finite element analysis is also known as finite element method. It is a numerical technique to obtain approximate solutions of boundary value problems. Let us first see two simple examples of boundary value problems and review some of the basic terms associated with these. Let us first consider one-dimensional steady-state heat conduction problem. Consider this rod where the left end is maintained at a temperature T is equal to T1 and the right end is maintained at a temperature T is equal to T2. The length of the rod is L and the problem is to find the temperature T at any location in the rod. We can take this as the x-axis and the left end is x equal to 0 and the right end becomes x is equal to L. To solve this, we should first mathematically formulate the problem. The mathematical formulation will include governing equations and boundary conditions. We know that if the rod is initially at some temperature and when both ends are maintained at T1 equal to 30 degrees Celsius and T2 is equal to say 70 degrees Celsius, there will be heat transfer from higher temperature to lower temperature, that is from the right to left end. And eventually the rod reaches a steady state, that is at any location the temperature doesn't vary with time. After that there will be steady state heat transfer from 70 degrees Celsius to 30 degrees Celsius. The three-dimensional steady-state heat conduction equation is dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square is equal to 0. And we have also assumed that the thermal conductivity K is a constant here. Since the problem is in one dimension, our equation now reduces to d square T by dx square is equal to 0. Solving this equation will give you T, the temperature, as a function of x. Here x is called the independent variable and T is known as the dependent variable. These types of problems are sometimes known as field problems, so T is also known as a field variable. Also notice that the equation in 3D was a partial differential equation and the 1D equation is an ordinary differential equation, because since there is only one independent variable x, we don't require partial derivatives. Now the boundary conditions. Boundary conditions are the value of the dependent variable or the field variable at certain values of x, that is the independent variable. Here at x equal to 0, the value of T is equal to T1 and at x equal to L, the value of T is equal to T2. These are the boundary conditions. Solving this is simple. We have to integrate the governing equation twice. If you integrate it once, we get dt by dx equal to a constant C1, and if you again integrate it, we'll get T is equal to C1 into x plus C2. To find C1 and C2, the constants, we'll apply the boundary conditions. The first condition is at x equal to 0, the value of temperature T is equal to T1. So let us substitute that. So the temperature T is equal to T1 at the value of x, C1 into x equal to 0 plus C2. This implies that the value of C2 is equal to T1. Now the second boundary condition is at x equal to L, T is equal to T2. So let us substitute that. T is equal to T2, that is equal to C1 into x, that is equal to L, plus C2. C2 we have already got as T1, so plus T1. This gives you the value of C1 is equal to T2 minus T1 divided by L. So we can write the solution as T is equal to C1, that is T2 minus T1 divided by L into X plus C2, that is T1. So to summarize the basic terms, we have seen that X is known as the independent variable, T is the dependent variable, next the governing equation, and governing equation is a differential equation, then the boundary conditions. Here what we specify is the value of the dependent variable T at some value of the independent variable, say X equal to 0. This type of boundary conditions where you specify the value of the dependent variable are known as Dirichlet boundary conditions. Dirichlet boundary condition. Now the solution. What we have here is known as a closed form solution, which means the dependent variable T is expressed as a function of the independent variable. Here T is equal to T2 minus T1 by L into X, X is the independent variable, plus T1. This closed form solution satisfies the differential equation at all values of X. Satisfies the differential equation, that is d square T by dx square is equal to 0 at all values of X. Also, if you consider this road, we can find the value of the temperature T continuously at any value of X using the solution. The solution is also known as analytical solution. Analytical solution. Okay, now let us see another example